sklearn, manifold, SMACof. Description. The SMACof scaling by majorizing a complicated function algorithm is a multidimensional scaling MDS technique for finding a low-dimensional representation of data that preserves the pairwise distances between data points as much as possible. Inputs. Distances: a distance matrix representing the pairwise distances between the data points. The input can be a condensed distance matrix, a 1D array with distances between all pairs, or a square distance matrix, a 2D array where distances between points are stored. Metric: a Boolean value indicating whether the input distances are metric true or non-metric false. If metric is true, the algorithm assumes that the distances satisfy the triangle inequality. If metric is false, the algorithm tries to find a representation of the data that minimizes the stress function. N components: the number of dimensions of the embedding space. Init: the initialization method for the embedding. Possible values are: random, initialize the embedding with random values. PCA: initialize the embedding using principal component analysis. A ND array: initialize the embedding with a specific ND array. Ninit: the number of different initializations to try. Outputs: embedding: a 2D array representing the embedding of the data points in the low-dimensional space. Each row corresponds to a data point. Stress: the stress value of the embedding, which is a measure of the goodness of fit. Lower stress values indicate better fits. Steps. Initialization: the algorithm starts by initializing the embedding of the data points in a low-dimensional space. Iteration: the algorithm then iteratively updates the embedding to minimize the stress function. The stress function measures the difference between the input distances and the distances in a embedding space. The algorithm uses a majorization technique to minimize the stress function. Metrics. Stress: the most common metric used to evaluate the quality of the embedding. It measures the difference between the input distances and the distances in the embedding space. Lower stress values indicate better fits. Shepherd diagram: a visualization tool that plots the input distances against the distances in a embedding space. Visualization plots. Scatter plot: to visualize the embedded data points in the low-dimensional space. Shepherd diagram: to visualize the relationship between the input distances and the distances in the embedding space. Fine-tune parameters. N components: the number of dimensions of the embedding space. Increasing the number of dimensions can improve the quality of the embedding but can also make the algorithm more computationally expensive. Ninit: the number of different initializations to try. Increasing the number of initializations can help to avoid getting stuck in local minima. Metric: this parameter influences how the algorithm interprets the input distances. Setting it to true means the algorithm assumes the distances satisfy the triangle inequality. Challenges and fixes. Challenge 1: getting stuck in local minima. Sample use case that resulted in challenge 1: if the algorithm is initialized with a poor starting point, it may get stuck in a local minimum and not find the best possible embedding. Fixes to challenge 1: try different initializations using Ninit. Challenge 2: long runtime for large datasets. Sample use case that resulted in challenge 2: when processing a very large dataset, the algorithm can take a long time to run. Fixes to challenge 2: you can consider using a dimensionality reduction technique, e.g. PCA, to reduce the dimensionality of the data before applying SMACof. Uncertainty methods. Bootstrapping: repeatedly resample the input data with replacement and then fit the SMACof algorithm to each resampled dataset. Jackknifing: remove one data point at a time from the dataset and then fit the SMACOF algorithm to the remaining data points.